Hello everyone, welcome to Pratibha Tech. In this video, we will solve the problem of the day question on GeeksForGeeks for 9th May 2023. The problem statement for today is count binary strings with no consecutive ones. Let's now open this problem to solve it. Let's go through and understand the given problem statement. Here it says, given an integer n, your task is to find the number of binary strings of length n having no consecutive ones. As the number can be large, return the answer modulo 10 to the power 9 plus 7. So here the problem statement is simply asking us to find the number of binary strings that is having length as n, but it should not have any consecutive ones. So for example, first example here it is saying n is equal to 3. So the length of the binary strings should be 3, and we have to find the count of the binary strings where no consecutive ones are there. So the output here is 5. So all the binary strings that is having no consecutive ones are all of these 0 0 0 0 0 1 1 0 1 1 0 0 and 0 1 0. When we look at the second example, so here the output is so here the length is 2. Here the output is 3. All the binary string of length 2 having no consecutive ones are 1 0 0 0 and 1 and 0 1. Okay, so I hope the problem statement and the given examples are clear. So before moving to the solution or the approach of it, so let me go to notepad. Here I wanted you to visualize this one or observe this one. When we talk about the binary strings of length 1 where we do not have any consecutive ones, so here the possible combination is either 0 and 1. So here the count is 2. When we talk about length 2, as we have seen in the example, here we are getting all these 4 combinations 0 0 0 1 1 0 and 1 1. Since we have to take only those values where consecutive ones are not there, that's why we are discarding this 1 1. So total count is 3. When we look at length 3, then we get these many combinations. All these, there are 8 combinations. But among these 8 combinations, in 3 combinations, we see that consecutive ones are there. One is this one is this one, and one is this one. So we are leaving out them, remaining all others we are counting, and the output is 5. So similarly, if we look at 4, then it will be, the count will be 8. For 5, the count will be 13. Okay, count will be 13. So here what exactly is happening, if you see this pattern, it is 2 3 5 8 and 13. That means to get the value of the current value, we are adding the previous 2 values. So when we had for length 1 we got 2 count, for length 2 we got 3 count. When we add these 2, we got for length 3, that is 5 count 5. For length 4 we got count as 3 plus 5, that is 8. So similarly, the problem is asking us to find the Fibonacci series of nth terms. But here the problem is that that is having so much of that is not optimized. That when we try to find that nth term of Fibonacci series, and when n will be very large, so it can give the heap and that memory out of bound issue. That means some memory issue or the time complexity issue. So we have to solve it in some different approach, using some different approach. Okay, but the output will be similar to that only, with that approach only. Okay, where we just find the Fibonacci series of the nth terms. But for finding the Fibonacci series of nth terms, we will be using a different approach, and the approach which we will be using is based on the idea of matrix exponentiation. A matrix can be used to represent the number of binary strings of length 1 that do not contain consecutive ones, and then we use matrix exponentiation to compute the number of binary strings of length n that do not contain consecutive ones. So the matrix used in this approach is of 2 cross 2 matrix. Here whatever we are seeing here, 2 cross 2 matrix, that is of 1, 1, 1 and 0. Okay, the ijth element, that means here this element in this matrix, that is represented by some value of I and some value of j. Here ij will be 0, 0 in this one, which I have written below. So I and j will be 0, 0 for the first element. So the ijth of the element represents the number of the binary string of length 1 that end in a j and do not have any consecutive ones, and the previous digit is I. So here we have to find those many combination where the ending digit is j, that is 0, where we do not have previous where the previous digit is I. So we get this combination, that is 0, 0. So that how many, so that count here, so that is possible. Only thing we have to discard is when two ones comes, then we do not have to count them. So with this, where the value is ending at 0 and previous value is I, so we have one value there, that is valid. So that's why 1 it is here. When we move to the second value, here it is 1. So this is represented by j that is equal to 1 and I is equal to 0. So here it should end with j, this one. That how many such counts where it is ending in j is equal to 1 and having I is equal to 0, that means 0, 1, and this combination is there. So again we are getting count as 1. When we look at this one, so here I is 1 but it is ending at j is equal to 0. Okay, ending at j and having the previous value as I, so 1, 0. So for this combination, how many items are there? 1. How many combinations are there? 1. When we look at this one, ending at j and having previous value as I, so here both I and j both are 1, but we do not but we cannot take this because here it is 2 consecutive ones are there, that's why the count it is 0. Okay, so we are getting this matrix here. Now to compute the binary strings, to compute the number of binary strings of length n that do not contain consecutive ones, we can compute n plus 1th power of this matrix. That means we can multiply this matrix with itself n plus 1 time. Okay, so this itself is called as matrix exponentiation. You can multiply it with itself n plus 1 times, or you can take a power of n plus 1th power of this matrix. Okay, so in that matrix, the resultant, the 0th element of the resulting matrix will give the number of binary strings of length n that is ending at 0 and do not have any consecutive ones. Okay, so that will give the output. So here we have to find, in the first example we have to find for n is equal to 3. So what we are doing, if we see this one, this matrix, whatever we have got 1, 1 and 1, 0, this we are first multiplying it with itself. Okay, so multiplying it with itself, it will give the value as 2, 1, 1, 1. Here it is between all these numbers, here it is 1 into 1, 1 into 1. So that is understood. So here we are getting 2, 1, 1, 1. So this was for n is equal to 1. Okay, so that is where you can see whatever is the 0th value that we are getting for n is equal to 1. For n is equal to 2, okay, n is equal to 2, what we'll do, we will, with this value, we will again multiply this matrix. So whatever is the value what we have got in this, we are multiplying with this matrix. So we get this value 3, 2, 2, 1. So again the first element in this matrix, that is 3. So that represents the number of count is equal to 3 when n is equal to 2. When we are multiplying it for 3 times, that means again what we'll do, with this resultant we are multiplying it again, this one. So we will get this value 5, 3, 3, 2. So whatever is that first element in this matrix, that will give the value as 5. When we multiply it again, it will give for 4. So here the first element in this matrix, that will contain 8. When we multiply again, it will become 5. sorry, yeah, here it will give 13, and that will be for length is equal to 5. Okay. So what we are doing, we are multiplying it with we are multiplying it to itself n plus 1 times. Why it is n plus 1 time? Because see, to the resultant we are multiplying it with this matrix, but initially both are the same. So for the first time both are multiplied among themselves, so that's why here only 2 times it is calculated. With this resultant we are calculating it, we are multiplying it again. With this resultant we are multiplying it again to get the result one. So for n is equal to 3 we are multiplying this one 4 times. Okay. So another better approach for just multiplying this one, here when you multiply this n times, so n can be very large, so that time it will give some TLE issue, time limit exceeded, that issue. So one thing we can avoid that, we can avoid, and we can try a different approach. So what we can do, once we have multiplied both of them together, that is among themselves, when we are getting this output, then what we can do, whenever that number of count is odd, even, that means whenever the number is even, what we can do, so that time instead of multiplying it with 1, that means 1 1 1 0, this matrix, what we can do, since we are for between each two events the multiplication would be happening for twice, that's why we will multiply this with itself. So what I am saying is that instead of multiplying this matrix with this, we are getting this, and again multiplying this with this resultant, why don't we multiply this to itself, so that we directly get this value. So with that only I have done here. So whenever here when we have multiplied it among itself, that we multiply this matrix with itself, we got this one, that means two such matrices are multiplied with itself. Okay, so we got this value. Now to this, if you multiply it itself with itself, then we can say that this matrix is multiplied 4 times. I hope this is clear and this is observable. Okay, so even this is also same. If I directly do it here, if I directly move here only, this one, if I directly move this one here, then even second part would give the result this only. So it will again be like multiplying this matrix with this. Okay, so I hope this is clear. So we will be following that approach. Whenever it is even, that time only we will multiply. Whenever it is odd, that time we will not do anything. We will just multiply it with the identity matrix, so that we get the value same. So that way we will reduce the number of multiplication that will be happening. Okay, so that we will skip some TLE issue. I hope that is clear, because multiplying it with identity, that will not take that time, and we will just get that value there. Okay, so with this one, so with this approach only, let's start coding part of it. I hope the solutions is, and that means the approach is clear, what exactly will be done. So let me just copy first Java code to it. Here again I have given comments in detail, so that it becomes easy in understanding. So here what we are doing, first we are initializing the modulus function, because here it is said in the problem statement only, as the number can be large, return the answer modulo 10 to the power 9 plus 7. So that only we have taken here. So now whatever this function was there, so this function is taking long n as the length of the input, the length of the binary strings that we have to find, which is satisfying the condition that no consecutive ones are that means there shouldn't occur any consecutive ones. Okay, so what we are doing here, we use matrix power to find the value of function of n plus 1, where f of I is a Fibonacci number. As I said initially while explaining the approach, that here it is just like calculating Fibonacci series of nth terms. Okay, the number of binary strings of length n without consecutive ones is just the n plus 1th Fibonacci number. Okay, but we use matrix power to compute f plus 1 f plus 1th term of the Fibonacci series, since the matrix representation of Fibonacci number has a property that can be used to compute them efficiently. So we will not get the TLE issue there. Okay. So what we are doing, I hope this is clear now. So we are calling this matrix power method. We are passing that matrix, this one, matrix with that yeah, here we are passing this 2D matrix which we have seen in this example, the first one here, 1 1 0 1 1 1 0, and we are passing the length, that is n plus 1, and whatever is the value returned out of it, we are getting the first element as 0 0, as I have shown here, that whatever was that element, that means the result of the multiplication, for that for n is equal to that n, we are taking the first one, and that is the output. For n is equal to 3, we are taking this first value, for that is the output. For n is equal to 2, this first element, that is the output. So what is that index variable of this one, value of this one? This is 0. This is occurring at position 0, 0. So that's why we are taking 0 0 of whatever the matrix that is returned from this matrix power. Okay. Now inside this one, inside this matrix power function, we compute the power of the matrix. In the code, the function takes the matrix A and a long integer n as input and returns the nth power of the matrix A. The function here uses while loop to repeatedly multiply matrix A with itself. Then update the value of n by dividing by 2 until n becomes 0. If the value of the n is odd, the result is multiplied with the current value of A. Finally, the resulting matrix is returned. Okay, and for multiplying this one, we are calling this multiply matrix this method. So this multiplication matrix multiplication operation is used to multiply two matrices. Here we are calling this method, that means multiply matrices, takes two matrices as input and return their product. The matrix multiplication is performed by iterating over the rows and columns of the result matrix and then compute the dot product of the corresponding rows of the first matrix with the corresponding column of the second matrix. This is the simple the matrix multiplication what we do. So this multiplication, after that it will return the value in this form of this matrix. Okay, so again multiplying this A with itself, that we will only do here, that we will do when n is equal to even. That means here we are calculating that itself with itself. Okay, that means multiplying that A into A with itself. So we get the updated value of A, and we reduce the value of n by dividing it by 2. Okay, so this way we will calculate efficiently the n plus 1th term of the Fibonacci series. This is much efficient because this takes only big of log n time. That I'll explain in the time complexity how much it is. But before that, so this was the coding part of it. I hope the solution is pretty clear, that what is the logic behind taking this matrix, why we are taking 0 0th of it, and why we are not directly following the Fibonacci approach. So because that was giving, I tried initially with that only, but that was giving some heap issue, some memory issue, because that was going so long for the large value of n, up to 40 50 or something which I tried in lower in number. That time it was working fine, but once it started becoming the n becoming large, then it started giving that issue related to memory. Okay, so this was the solution in Java. Let me try compiling this code. Something. Okay, I have not copied it correctly. So here we can see we have got correct output for this given input as 3. So even if I try with some other, if you try with 5, it should give 13. If you try for 6, So it will give 13 plus 8, 8 plus 13. So it will be 21. So see, this one is actually printing the Fibonacci series of nth plus 1st term only. Yeah, but we are solving it using matrix exponentiation in an effective way, which is taking very less time. Okay, so let me try submitting this solution now. So here we can see it has covered all the test cases. So this problem has been solved successfully in Java. So when we talk about the time complexity of the solution, it is in the order of log n, because the matrix power function uses the binary exponentiation algorithm to compute the matrix power, which takes big O of log n time. The matrix multiplication function takes big O of 1 time, since the matrix size is fixed, that is 2 cross 2. Therefore, the overall time complexity of the algorithm is dominated by the matrix power function, that is giving a time complexity of log n. Okay, so this was a Java solution. I have even prepared C++ solution. The logic is completely same, only the syntactical difference between C++ and Java. With that, the solution is here. Okay, so let me just take it. This function is getting closed here. Okay, so this is fine only, but let me take it above. Yeah, so again here also we have defined this modulus, and we are calling this matrix power. We have defined that matrix 1 1 and 1 0, and we are passing this matrix n plus 1, and inside this one we are multiplying this matrix with itself, and whenever it is odd, then we multiply that A with result. And for multiplying this matrix, we are calling this function, and this is just doing simple matrix multiplication. So here it is like just we are computing A to the power n plus 1. So this matrix to the power n plus 1, so that this matrix is multiplied to itself n plus 1 time. Okay, so the logic is completely same. I am trying compiling this code. So here also we can see we have got correct output. Let me try submitting C++ solution. So even with this C++ code, it has passed all the test cases. So this problem has been solved successfully using both C++ and Java language. So I'll provide the link for this question and the link for the solution code in Java and C++ in the description box. Please do check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.